In this video we're going to consider some alternative expressions for acceleration that are just going to allow us a bit more flexibility when we're working with equations of motion. So we're already familiar with a couple that we've been using for quite a while, and those are the idea that acceleration is the derivative of velocity with respect to time, and that acceleration is the second derivative of position or displacement with respect to time. And immediately the thing that's related between both of those is the concept of time. That if we differentiate with respect to time, we can find those. So they're really useful when time is one of the variables that's involved in our considerations. So if we've got equations expressed in terms of time for position or for velocity, that's really useful. But that won't always be the case. And so our formula sheet actually gives us a couple of other expressions. So we don't have to remember these. There's the first two, a equals dv dt, which is equal to d2x dt squared. But then it suggests that acceleration can also be written as v dv dx, or even as the derivative with respect to x of a half v squared. And the thing I want to draw your attention to straight away with both of those expressions is that t doesn't feature in there. Alright, before we talk about how we might or where we might use those, let's just quickly check that we can develop both of those. We don't need to be able to because they're given to us on the formula sheet. But okay, if we start off with this one here, that acceleration is equal to dv dt, let's simply do a chain rule sort of expansion on that there. So let's say that's dv dx by dx dt. Hopefully we're fine with that as an expression of the chain rule. But then notice that this one here, dx dt, that's actually just velocity, isn't it? So if I replace that with v, then I've got dv dx times v, which I could write as v times dv dx. So that's that one there that I've got simply from applying the chain rule to this one here. So where's that useful? Well, it's not completely cut and dried, but typically it's useful when we're given acceleration as a function of velocity, so an expression for a in terms of v, and we need to relate x and v. We need to relate position and velocity. So notice in there, there's nothing sort of to do with time. We don't need to find where is it at a certain time, but we might need to find how fast is it going at a certain position, or what's its position at a certain, when it's traveling with a certain velocity. Alright, what about this other one here? Well, this one's actually probably a little bit easier to sort of show in reverse, but we can show it kind of this way if we start off with a little observation, which isn't completely obvious, but that is that velocity could be written as the derivative with respect to velocity of a half v squared. So in other words, if I differentiate this with respect to v, I'm going to get 2 times a half v to the power of 1, which is in fact just v. So it's not sort of an immediately obvious thing to do, but hopefully when you look at it, you can say, yes, that's definitely true. So now what I'm going to do is I'm going to take this as an expression for velocity and substitute it into this expression here for acceleration. So when I do that, I get acceleration is equal to velocity, this v here, which I'm replacing with that, times dv dx. So v times dv dx is this times dv dx. And then what I can observe here is, using the chain rule, I've got d dv of this here, that could be, du dv times dv dx, is just going to be d dx of this here. So that's using the chain rule sort of the other way. I can say it's d dx of a half v squared, so that's that one there. Well, this one here, typically useful when acceleration might be given as a function of displacement or position, and we need to relate x and v. So again, where t is not involved. Alright, let's think about an example where we might use that. Here's the first example from exercise 14c. An object travels in a line such that the velocity is given by v squared equals 9, take x squared. Find the acceleration at x equals 2. So notice in all of that question, there's nothing really related to time. So we're given velocity as a function of position or displacement, and we're asked to find acceleration at x equals 2. So we don't even really need to know anything about time. We don't need to know, at what time does it reach this point, at what time is its velocity, any sort of value and so on. So how could we go about doing this? Well, with this one here, you might say it doesn't quite fit into either of those typical uses because we're not given acceleration. So let's in fact see how we could sort of use either of these in this particular case. So I've got v squared equals 9 minus x squared, don't I? So I'm going to show you we could go either, and then we'll do an or. So either we could say a is equal to d dx of a half v squared. So since we're given v squared, that's going to be d dx of a half times 9 take x squared, isn't it? So we're just replacing 9 take x squared, or replacing v squared with 9 take x squared in that expression. And then I could take the constant out the front, couldn't I? So half d dx of 9 take x squared, which is going to be half of negative 2x, which is just going to be negative x. So we're trying to find the acceleration at x equals 2. So at x equals 2, the acceleration is going to be negative 2 meters per second squared, just subbing that into the expression that we found. So that's one way that we could go about that. The other is to say, well, let's start with our expression v squared equals 9 take x squared, and then just differentiate both sides with respect to x. So there we go, differentiating both sides with respect to x. And then use my chain rule here on the left-hand side. So I could say, let's change that to, so can we see that I've just changed the d dx to a d dv by dv dx. So if this was like du dx, it's now du dv times dv dx. And on the other side, when I differentiate that with respect to x, I get that. So on the left-hand side, we're going to differentiate v squared with respect to v, which is 2v. So 2v dv dx equals negative 2x. Dividing both sides by 2, we get v dv dx equals negative x. And v dv dx is, in fact, an expression for acceleration. So we can say, therefore, a equals negative x. And then we could make the same conclusion there from, so let me just, in fact, move this over here and say whichever way we've gone, we can then come up with that same result for the acceleration at x equals 2. So it's just one example, and the question's going to look fairly different. Different questions will look different, but the big thing to notice here is that t is not involved. And so we need to be careful if we're given an expression for acceleration or velocity that doesn't involve t, because then we may not be using our more common expressions for acceleration.